we will see some of the things which is in metallurgy and metallic areas in this session. And most of the things we will not be covering the basics of the composite material, polymers, plastics. We will not go to polymer and plastic side. So mostly we will try to be in metallic side, polymer side. Other talks in our upcoming sessions will be covered. So we are moving into the area of metallurgy and material science. So according to me, there are one of my professors at IIT used to say there are only two things in the world: one is spiritual, other than spiritual. Everything else is materials. So we are coming in materials era, and most of the attendees, I hope they are mechanical or chemical or production based people. So let us give some introduction about the metallurgical and materials of the composite material. Then we will go to one or two case studies of the composite materials and scopes and opportunities wherever possible and in this possible time. So first, some few slides I will be covering a syllabus of metallurgy for non-metallurgist or something like that. Before going that, let us ask a question. See this, there is natural structure and man-made structures. We all make structures, whatever may be the engineering, even let it be in electronics engineering. They have to be deal with electronics materials. So materials is part and parcel of every part of every section. So in this case, let it be electronics material or electrical conductors like copper and aluminum, what we use, or let it be a material which is used in civil industries or mechanical or core metallurgy. There are two things. We are using some of the natural materials and some of the man-made materials. But look at the natural materials. Few natural materials with crystal structure. We will just see what is crystal structure, crystalline materials, etc. in a few more slides. If you look at them, for thousands of years, they don't have any deviation in their properties. And their repetition is perfect. As well as these two are perfect, automatically their quality is perfect. But whereas, for example, if you make a material for an aircraft, let it be composite or non-composite, 60% of the money is to be spent for testing. You have to make sure that every batch or every piece or every part is tested, proved, and clarified. If not, it is not fit for flying. Why so many irregularities? That's because we have to start from atomic level, and the perfection is attained. Yes, then our material also will compete with the natural materials. Okay, and some of the words we might have seen, for example, in the last 15 years or even 20 years before, everything used to be nanotechnology, nano-based. Let us start our research in nano. That's what used to be buzzword. It's almost settled now. But is it anything new? Are we not using any nanomaterials? We are using nanomaterials in day-to-day life also. You are also using, I'm also using. So we will come to that. What all are the nanomaterials we use? Nanostructures, nano coatings. Is there any example right now? Yes, you take your SIM card or any electronic gadget. You can have a nano coating, nano gold coating on the structure. Hope you know why it is gold coated and why it is nano gold. One is for technical reason, another is for commercial reason. Why it is in nano size, it is for commercial reason. Okay. So are we not using any composite or any metallic ceramic? Yes, we are using. Hope if you talk about the carbide tool, what exactly is a carbide tool? That also we'll see. Carbide tool doesn't mean that it is only carbide. It is a composite. It is a perfect case study and perfect example for a metal matrix composite. Okay, few more nanomaterials. Why are we talking about these particular materials? Because they are part and parcel of the composites. Let us say, when we are talking about the composites, we are talking about the matrices, and reinforcements. Sometimes we call reinforcement as fibers, and we are not worried about the fillers, all other things for the time being. So let us talk about the matrix. Anyway, it is a large structure, we know it. And now let us talk about the fibers or reinforcement. If you take just a simple example, if we take a garden hose, a braided garden hose, which is available, most of the houses it will be available, not the plain polymer hose. You take a braided hose, you can see a bunch of glass fibers embedded in it. If you take out that bunch and if you take an individual glass fiber, that is near about nano size. Okay. So when did we think we use glass in day-to-day? We use mirror, that is silica based. And when you go for industrial glasses or glass fibers also, it is similar. There are some additives added to that, but the majority of the composition is still silica based. But did you ever think that how to make a glass flexible? To some extent, it is ductile also. To some extent, it's not as brittle as we see in uh, home mirrors. How do you make that? Or if you are in and around Chennai, Saint Gobain manufactures automotive glass. What is the procedure of manufacturing a glass? It's simple. If you have an equipment, thermal equipment, which can heat about 1400-1500 degrees Celsius in a small scale, you also can make glass fiber. And other example, anyway, high strength steel fibers. Most of the time, you might have seen steel ropes. Simplest example for this composite is you might have seen the power transmission line outside. When you see a power transmission line, high HT lines, you can see an aluminum conductor. And if you cut the aluminum conductor and see inside, there is a high strength steel fiber, high strength steel core is there. It is a typical example for another composite. The steel is inside, then the aluminum wires are outside. Why it is in wire, why it is in a rope shape, you know that it should not be a single piece due to its flexibility necessary. But why do we keep a steel fiber inside that? That's because the aluminum takes conductivity, but what will take strength? The aluminum lines will say, if you install aluminum lines as such in between two pylons for a transmission line, probably in a week time it will touch the ground. So there should be something to take care of the strength. That's what is steel. But there should be something to take conductivity. That's what our main aim. Strength is not the main aim. Conductivity is the main aim. That's where aluminum is used. This is a combination of a conductor and a strength part. It's a composite. We don't have any other option. And you might have seen wind turbine blades. If you are somewhere near Palladam, Coimbatore region or in a Kanyakumari, Tirunelveli region, you might have seen the 2 megawatt and above windmills. For installation of the windmills, they might have transported the blades. Blades is factory made. It's not that the structures or pylons which are made in situ, but unfortunately the blade is to be made in factory. It is another example for a composite. It's such a lightweight item. We can't make in any other material other than a polymer composite. Hope we are familiar with all these words like polymers, glass fibers, carbon fibers. These are, we handle the composites in day-to-day life many times. We handle the metallics also in many times. And some of the manufacturing, we are yet to know. So we'll see that things. This is the typical common example for composites. I put only partly, that is mostly on metallic side, not on polymer side. These are the composites. There are few polymer examples. One is copper bottom vessel. You might have seen vessel in your home. Few stainless steel vessels are copper bottom, copper coated. There are few questions on this. First of all, how do they put that copper bottom? What is the process of manufacturing? Second, why do we put copper? Why are you giving a copper bottom? Third question is, why a stainless steel and copper are separate? Why can't we make a copper stainless steel alloy? The work is finished. Is it not? Then aluminum conductor, I just explained. Teflon coated utensils. Though metallurgically the Teflon coated items are not suitable for Indian cooking style, we are overheating it. But Teflon coated utensils, non-stick tawas, all non-stick utensils are other typical example of a composite. It's a metal polymer composite. Is it not? A metal item is reinforced. Polymer is outside. Then nano gold coated SIM card. Tinned copper wire. You might have seen some of the copper wire only at the edge. It is in a gray color. That is a tin plated one to avoid oxidation. Only at the edges. If it is a long cable, 1 kilometer long cable, and the insulation. With the insulation, the copper cable itself is a composite. But when we see at the end, it is a tin coated. Another typical example, earth moving equipments, if you see any book lanes, There's a high wear and tear, is high wear rate, is it not? To have a longer life, only the shoots, only the place where we are facing the high wear is welded with some hard metal items by hard facing, weld layering, anything. And see, if you take anything, so for example, pressure cooker, if you take, there are three parts. It's an aluminum pressure cooker with a polymer gasket, with a backlight handle. As a whole, it itself is a composite. Another typical example is ballpoint pen. What is the ballpoint pen ball made up of? It's a tungsten carbide. And tungsten carbide, if you take only the word tungsten carbide, it is ceramic, but not actually. Tungsten carbide alone cannot do any engineering work. It is a composite. It is embedded in cobalt, that we will see later. Like that, there are many things. The typical example, bulletproof glass or bulletproof steel armors. There are two things. Few people use glass, few people use steel armor. That must be a composite. And even nowadays, bulletproof glass vehicles are sold for commercial purpose also. So what is the glass? How the glass is made? It is a typical same glass what you use in our car and your car. It's not a different. Only thing is it is a manufactured as a composite, that's all, with a polymer film in between. Silk saree. That silk saree. Silk is another typical example of a composite. Silk. Then on the top of the silk, it is a silver foil. On the top of the silver foil, it is gold coated. Gold jewelry. Most of the gold jewelry used to be composite. We will come to that later if time permits. Fuels, solid fuels in rockets. You might have seen when we launch satellites, there is a small 3-4 solid rocket motors surrounding it. What is the fuel used in? It's a solid fuel. What is that solid fuel? If time permits, please find out that. It is a metal combined with some polymer in a powder form. This is a slightly upgraded version, like our firecrackers. These are examples. The last one is anyway braided hose. This is what I was telling. Nano glass fibers. Okay. And composites in strategic sector, something like in space, aerospace, nuclear. What all are they used? So these are few words. We will try to learn 1 or 2 case studies, but these are few words. One is tungsten alloy. Hope we are aware about the tungsten. It is used in filaments. Tungsten alloys are famous for very high density and very high temperature of application, but unfortunately in a controlled atmosphere. Superalloy. The name superalloy is, this is a colloquial name. Superalloy means an alloy which can operate in any environment at 700 or above 1000 degree or above 700 degree. So naturally the application comes to aircraft engines. Maraging steel. Hope if you have not heard that word, this is nothing but if you see any satellite launch from particularly Indian side, what you see in a TV, or if you, some of you might have witnessed it, the round structure what we see, what is that material? What is inside and what is the fuel and how the satellite is assembled? Forget about those things. Only the pipe is made up of maraging steel. Okay, and superalloy already told. And another thing is titanium alloys. Hope what for we use titanium alloy. It is also semi-aircraft application. Titanium alloys are famous for lighter weight. For example, if we take any superalloy or any steel, the density is around 8 gram per centimeter cube, whereas titanium is just half of that. Okay, some of the copper alloys. And when we come to aluminum alloys, we all know, if you particularly zero it on an aluminum alloys for aircraft application, it is a 2 series or 7 series. That means aluminum copper alloy. It's the lowest density. Further down to aluminum alloy, there are polymer composites, carbon-carbon composites, and carbon polymer reinforced, carbon fiber reinforced composites also. We are not touching that, but they are even lower density material than aluminum alloys. But this is the workhorse for a long 100 years. Aluminum has been ruling the aircraft engine industry. And here you have to please note on this, aluminum alloy is only for aerostructures, fuselage, whereas super alloy is for aero engines. There's a difference between these two alloys is huge. One is for very high strength, lightweight, low temperature application. Another one is very high strength at very high temperature, super alloy. So this is engine, this is body. So if you see in a local colloquial language. Yes, when we talk about all these materials, then naturally comes how do we make this material? What is the procedure? What is the difficulty? For example, if you take only super alloy, which is used to make aero engines, there are only 3 companies in the world can make aero engines. Hope you are aware that Pratt & Whitney, GE, Rolls-Royce. There are only 3 companies who can make aero engines even today. It's 2021, June 1st. Whereas the Boeing, if you think that Boeing and Airbus make engine, no, they are aircraft manufacturers. So why only 3 companies can make? Why don't we make it? Is there any company we make aero engine, whole aero engine assembly in India? Yes, we are still struggling. Why? Simple, it is materials. Okay, so there are some other materials you have to remember. One is ceramics, another is cermet. Cermet is nothing but a ceramic plus metal. So automatically it is a composite. And anyway, polymer composites you are aware. And carbon-carbon composites. Ceramic matrix composites. There are a few other composites. For 1.5 hours only we can cover only this much. Okay, so now let us, with these questions, let us start the introduction. First, we should know about the materials. To know about the materials, we should know the classification of the materials. So first and foremost is metallic versus non-metallic. We classify the entire spectrum of materials into 2 things, metallic and non-metallic. We know in metallic what are the metals, alloys, and certain composites. And we know the example for metals: silver, copper, aluminum, nickel, tin, pure gold, not the jewelry gold, pure gold. Next is alloy. What is the example for alloy? Stainless steel, brass, bronze. There are many. Metallic composites, yes. Is there any example for metallic composites? See, we should link to any advanced application. First of all, we should know the basics. Second, then only we will be able to go for the advanced applications. Second, we should link everything to the material which is familiar to us and which we use at least once in a lifetime. So we talk about the metallic composite. Any example? Yes, typical example is your carbide tool. Another typical example is if we come across any repairing of the mixie, like DC motor powered items. If you take it for any repair shop, they might have simply told carbon brushes worn out, carbon brushes gone. What is a carbon brush? Or if you take any railway electric lines, you might have seen the railway electric lines are always in zigzag, and this pylon is touching that power. How much wear and tear is there, and what is the material used there? Those all are metallic composites. For example, if we take any carbon brass, we know the conductors are aluminum and copper. Is it not? Those are only 2 highly conducting commercial metals. Silver, copper, gold, aluminum, they are 4 best conductors. Out of that, forget about silver and gold. It's not a commercial one. So if you think about copper and aluminum, rest of the 2, copper is the best conductor among the 2. The copper alone cannot sustain certain conductivity application. For example, that is a typical example is carbon brass, which is used in mixie. It should have some wear resistance. Unfortunately, copper doesn't have. Something like previous example I told, the aluminum can conduct, but it doesn't have strength. So we are reinforcing with steel. That's why it is a composite. Like that, for a carbon brass, copper, metal, and carbon powder are mixed together and component is made. That's what is a metallic composite example. Another example, anyway, copper bottom vessels are typical examples. Okay, so metal versus non-metal. So metallic, I have given the examples. Non-metal, other than this thing, everything else, from polymer to anything glass, etc. This is one classification. Another classification, anyway, we classify into crystalline and non-crystalline. Other things like natural and man-made, let us ignore for the time being. And crystalline and non-crystalline, what are the other materials? Most of the metallic materials, except one, all other metallic materials are crystalline. That means they have a definite crystal structure. Non-crystalline may not have. So here comes the basics. That means, what is the difference between this and this? And what is common for this and this? Common is atom. Everything is made up of atom. And next to atom, what happens makes the difference of either metallic or non-metallic or crystalline, non-crystalline. Let us see that. So when we talk about the metallic materials, first thing we have to talk is atom. We are not going to split about the atoms. We are starting with the atoms only. So we know the definition of atom. And atom is common for metals and non-metals, crystalline and non-crystalline, both. Let it be, all the spectrum of materials are made up of atom. There is no doubt in this. Next to atom is unit cell. What is unit cell? If you are a mechanical engineer, if you recollect your third semester courses, unit cell is nothing but it's a combination of few atoms, but it's not a random combination. There is certain rules. And here comes the difference. Unit cell is available only in metallic and in few non-metallic. So all the metallic and few non-metallic items are with unit cell. And here comes the main difference. Crystalline means it must have unit cell. Non-crystalline, there is no unit cell. Then it is time to learn what is unit cell. So what is unit cell? Atoms arranged in a particular regular arrangement. That's what is unit cell. It's a regular arrangement, but it is the smallest possible regular arrangement, smallest size. That's what is FCC, BCC, HCP, all those things. So this is unit cell. So here it is regularly arranged. Next will be next unit cell, like that, like that, like that. The entire spectrum of materials with unit cell. This is what is crystalline and this is what is most of the metallics. Yes. Then comes grain and grain boundary. All other things like inclusions, additions, etc. let us see later, including the phases. What is phase? So next is grain. So what is grain? What is grain size? What is grain boundary? See, we know what is atom, we know what is unit cell. The thing is, if it is a crystalline material and if it is a metallic material, it is something like this. The atoms are arranged regularly. If it is a non-metal, unfortunately, there is no non-metal microstructure. The atoms will be arranged in random manner. Maybe in zigzag lines, a few lines like that. There is no regular arrangement like this. Okay. Now, we have to learn what is unit cell. Unit cell is nothing but some combination of unit cell and next is grain. Grain is nothing but the combination of unit cell and the same orientation. That means this is one unit cell, next will be here, next will be here, and this is the orientation. It is parallel to x-axis, is it not? One of this plane is parallel to x-axis. And when the unit cell forms, let us consider only metals and alloys. If you make the metallic materials, one of the route is melting and casting, etc. When these items are in liquid state, are the atoms arranged like this? No, they are random. There is no unit cell. So unit cell starts forming when the liquid starts cooling to solid. That's what is nucleation, you may be aware. When the nucleation starts, unit cell forms. First maybe this atom, then these all are atoms, then unit cell, then next unit cell, like that. But this may start and happen in multiple places. So multiple nucleations. Here is the trick. When the unit cell starts and next goes in this direction, there is a limitation. After a certain distance, the orientation cannot sustain in the same direction. Then the direction has to change. That is due to thermodynamics and a lot of other things, free energies, etc. So up to a certain domain or up to a certain volume, it is in three directions, all three directions, is it not? Up to certain distance, let us keep it simple, distance. Up to certain distance, all the unit cells are in only one direction. After that, then direction changes, let it be 45 degree, assume it, or 90 degree or some other degree. Then again direction changes, etc., etc. Finally, when the unit cells are all in one direction, one orientation, that particular volume is called one grain. Then next grain, and in between the areas grain boundary. Now you can understand the grain boundary is the area where unit cell has a lot of disturbances. One atom may be there, missing, one atom extra, etc., etc. That's what is given here. It's a schematic. So now let us assume only top view or any side view. Let us assume only top view of the unit cell. So you can see only the atoms like this. The green, blue, and red. I told you up to certain distance is only one same orientation. That only is grain. So one grain is here. Then orientation changes, next grain in between. This is disturbed area. So the atoms are disturbed like this. So this is the another schematic. In actual, it will be something like this. This is the actual picture, this is schematic. So now we know that what is unit cell, and we know that what is grain and what is grain boundary. And there is something called grain size. It is simply size of the grain. We will not go deep in that. And it may change. My material may have grain size of 2 micron, your material may be 3 micron. Those all are related to properties. So now what are we? Where are we? You know, atom, unit cell, grain, and grain boundary. Fine structure means if the grain size is a small, and coarse means it is a large. We know that. And this is common for metals and alloys. Is it not? It is common for metals and alloys. Metal also will have grain and grain boundary. Alloy also will have the same. Now in this material, if you add anything which will not part of the metal, then it is additions, inclusions, impurities, you can call anything. But still we left with what is that phase. We will come to that if time permits. So let us see actual structure of the metals now. So let us assume we are making an alloy with metal A and B. So if you consider the unit cell of metal A, there will be only one type of atom, is it not? There is only red atom. It is on the top view, let us say red atom. If you are allying with A and B, you know that not all the metals can be made into alloys. There should be some metallurgical, or there should be some thermodynamical characters fulfilling it. For example, if you want to make an alloy of A and B, A should be soluble in B, or B should be soluble in A, or both may be soluble in each other. At least there should be some solubility. So only milk and water can be mixed, can be made into alloy, something like, not oil and water. It will not mix. So solubility is must. Now let us assume we are making an alloy between two soluble metals, A and B. So this is only A. When you start making alloy, the structure will become like this. So what is that meaning? If it is a metal, unit cell will have only one type of atom, A, that is only red. So when you talk about alloy, when you start making alloy, few atoms of A will be replaced by B. That's what is seen here. Few atoms, not all atoms. And how many atoms? That depends upon the solubility. Maybe 1%, 2%, maybe 1 atom or 2 atom or 3 atom. There is a limit. That is a different case. There is a limit. So those many atoms will be replaced. Then it become alloy, and the name the picture says it is a substitution. That means one is substituted, so substitutional alloy. This alloy type is called substitutional alloy. So unit cell of metal A will have only one type of atoms. Now we made A and B as an alloy. It will have unit cell with a mixed atoms A and B, but still the unit cell should be there. And how many numbers of atoms will be replaced, that is depending upon the thermodynamics. Then next unit cell, all the things are same. This is what an alloy. When you say what is alloy, when we ask, the people say alloy is nothing but a mixture of two or more metals, they say. What is that mixture? I will give a metal A, small pieces, cut into small pieces, and I'll give metal B also cut into small pieces. I'll give a plastic box, put it inside and mix it very well and open it and see, will it be an alloy? No, not that mixer. Mixer is a colloquial word. Alloy is a solid solution. It is solid solution. It is made into solution. And mixer, if you use the word mixer in unit cell level, is it not? It should be mixed in unit cell level, not a simple mixer. Then only it is a really an alloy. So this is substitutional alloy. Example is silver and copper. Copper and nickel, brass, bronze, stainless steel, all those things. Okay, now you might have got a trick. See, when you want to make this type of alloys, the atomic size should be somewhere similar. It's not that exact, but similar. If it's a huge variation in atomic size, this alloy is not possible. Then there is another alloy that is called interstitial alloy. That means just look at this unit cell, there are a lot of gaps. Or look at this unit cell, lot of gaps, is it not? Unit cell is nothing but spherical shaped atoms arranged in some manner. Definitely spherical shape cannot occupy 100% volume, is it not? There are gaps. So if another atom can go inside the gap and sit properly, that is also an alloy. That alloy is called an interstitial alloy. That's what is steel. Carbon atoms will be sitting in the gaps. And there can be two, both the types also. So this is a metal, one alloy, another alloy, another alloy. Strength will increase like this. This is say 100 MPa. This will be 150 MPa. So 175 MPa, 200 MPa. Now you got another trick. We have metal. Wow, why unnecessarily we are making alloy? Can't we survive with metal? No, we cannot. Why? Certain properties. Strength will increase. Please recollect the basics. Strength of the materials are depend upon only two things. One is their crystal structure. That is what is this. Another is their microstructure. Microstructure is nothing but grain size. So crystal structure from like this to like this, if you make it, we cannot change that. Copper is FCC. Copper is always FCC. We cannot change. But we can make alloy like this. So strength increases. That's why we need to make alloy. It's something like coffee. We have sugar, water, milk. We can survive with all those things. But if you mix all the things, there are all these three and make an alloy. It's a solution if you make. It's tasting better, is it not? Like that, we need alloy for certain high strength application. And when I told high strength, automatically, we need metal for conducting better conductors. So metals are used somewhere, alloys are used somewhere. So this is an alloy, and how to make alloy? It is as simple as such. You heat it and melt it and make solid solution. I told the word solution. So you have to make it a solid solution. Solid solution making is possible only when you make it into liquid, is it not? So hope this alloy is understood. Now the word left out is phase. So what is phase? Phase is nothing but a chemically distinct homogeneous mixer. That means, let us say alpha phase. So alpha phase, what is alpha phase? You assume A and B, metal A and B. Pure A, that is FCC, is also an alpha. A, pure A means after, if you make an alloy, A will have certain amount of B, is it not? What is that certain amount? Up to solubility limit, is it not? How much amount of B you can add to A when you want to make alloy? There is a limit. Maybe 1%, 3%, 5%. What is that limit? Solubility limit. Something like it. How much sugar you can dissolve in water? There is a limit. If you dissolve excess sugar, it will come out. So up to that solubility limit, from pure A and up to that solubility limit, the unit cell characters will be somewhere similar. That means it will be FCC only. Only thing is, instead of pure, few atoms may be replaced. That's all. That is what is alpha. So don't get confused between grain and alpha. Grain is few unit cells. Let it be any metal or alloy. Few unit cells in the same orientation. Phase is up to certain composition. And when A has some certain amount of B, it is alpha. There is a reason why it is alpha, beta, gamma, etc. When B is up to certain amount of A, it is beta. So alpha and beta are vice versa. That's why there is an alpha in steel. When you see iron carbon diagram, you might have seen alpha. Is there any beta in iron carbon diagram? No. So what is our definition of alpha? Fe up to some certain amount of carbon. Fe is A, carbon is B. So Fe, that is iron is A, carbon is B. Iron with up to certain amount of carbon is called alpha. That means iron dissolved, the certain amount of carbon is dissolved in iron. Unfortunately, there is no beta. That means there is no iron that will dissolve in carbon. That is not possible, impossible due to that size. So there is no beta. If you see other brass, bronze, etc., there will be beta. If you see aluminum, copper, like that, there are many alloys which has alpha, beta, etc., etc. But in iron, there is no beta. This is what is the reason. There is only alpha. This is what is phase. So now we know atom, unit cell, grain boundary, phase, all these things. So why are we learning these things? These all are very important for understanding the metallic composites. So now we have seen alloy and we have seen alloy microstructure, and this is a microstructure which I have shown. Now let us come to this microstructure. See the gray and black. That means this is a grain, is it not? This is one grain. Grain can mean any shape. What is grain? We know these are a few thousands of unit cells are in the same orientation. Now you can see there are two types of grains, is it not? All gray grain and all the black grains. Grain boundary is not visible in this picture. It is somewhere invisible, but assume that there are grain boundaries also. Now, this is one phase. The grays may be alpha and the blacks may be beta. It's an assumption. Any two phases, alpha, beta, or alpha, theta, some two phases. That's why this color difference. And now you know that what is the alpha and what is the beta. For example, this is also I think alpha and Fe3C maybe. So different structures. So the grains are oriented in a different manner. You can see spherical, lathe-like, longitudinal, irregular, regular, small size, big size. These all are variations. But what is common is phase, atoms, unit cells, alpha, beta, etc., etc. Right? So this is the basics about the materials, metals and alloys, and certain composites. And these are another microstructure, brass, bronze, etc., only for understanding. Now, before going into composite, now let us learn how do we make metallic materials. First of all, metals are extracted. Let us not go deep in this. After extraction, if it is a metal or alloy, both are done casting. Why it is casted? That's what is only we give the shape. We know that. As a mechanical engineer, you know all the sequence: casting, machining, forming, welding. Where do we stop casting? Engines, like where do we stop machining? Precision parts. Where do we need forming? Shapes. Whenever we need shapes, we need forming. And why do we need welding? You know that. So these all are familiar. Now, there are certain other processes which should be familiar. First thing is powder metallurgy. So PMS, powder metallurgy. Another things are something chemical vapor deposition, physical vapor deposition, stir casting. These all are few words. Among these words, let us look only at the powder metallurgy. These all are only self studies. Chemical vapor deposition, physical vapor deposition. Okay. So if you cannot make certain material using this route, casting, machining, forming, welding, then you have to look at the alternative processes. One alternative process is powder metallurgy. One example for powder metallurgy is tungsten powder. What is tungsten? High temperature and high density metal. What is the melting point? It is 3400 something. Then we cannot do casting. Why? Because most of the casting operations are carried out below 2000 degrees Celsius. When you want to do casting, we know that we need a mold, we need a crucible. I told you alloy making is like coffee making. When you make coffee, you need a vessel to support it. Is it not? And the vessel should be inert to the coffee. If vessel dissolves in coffee and makes both the things are getting reacted and makes a new product, you can imagine the situation. So when you want to do casting, if you look at the foundry, there is something called ramming mass or crucible they talk. If you just take an example of jewelry making people may use a small graphite or clay graphite crucible to melt gold, is it not? And they will use a heat. Somehow we need a crucible, somehow we need a heat. So any crucible can withstand hardly 2000 degrees Celsius. But if you want to melt tungsten, which is melting at 3400 degrees Celsius, there is no possibility of making a crucible. Then the tungsten is made into powder, and the powder is made into some shapes, and powder metallurgy is nothing. It is only something like idli, dosa, chapati making. So idli, dosa, chapati cannot be made by a simple heating route like pressure cooker. You have to make it into powder, then you heat it. Same way, tungsten is made into powder and heated only up to something 0.6, 0.7 of the melting point in Kelvin. 0.7 into melting point in Kelvin, around 1800 to 2000 degrees Celsius, you can get the component. And this is the typical process to make any metal or ceramic composite. Why? When you make a composite, you cannot keep on melting it. And what is the alternative? It is only powder metallurgy. Powder metallurgy is what? Make the raw materials into powder, combine it, form a shape, then heat it to up to something half of the melting point in Kelvin. Then you will get the product. Right. So 5 processes. Then when you are not satisfied with all these things in terms of property, then you are doing heat treatment, surface engineering, any other ancillary process for the time being, which you will not go into deep in that. For example, typical example is say surface engineering. Why do you need surface engineering? Gear should be surface hardened. You know that it should not be, all things should not be hardened. So a gear, according to our talk, is a composite. It has a different properties at the edge and on the core, so it can be a composite. So we are yet to define what is composite, but this is an example for composite. Right? Now we are coming for composite. So what is a metal? We know it. What is an alloy? It is a mixer in unit cell level, I told, or it is solid solution. And what is a composite? That's what it is. Composite is also mixture of 2 or more materials. And that mixture is only physical mixture. There should not be any unit cell level mixture, or there should not be any reaction, nothing. It is only touching each other, that's all. That's what is composite. Now, why do we need composite? I told you, why do we need alloy? It is properties. Again, why do we need composite? Again, it is properties. Certain properties which cannot be fulfilled by metals, alloys, ceramics, only polymers, etc. Then it can be fulfilled by a composite. I already told you 2-3 examples. One is the aluminum tower lines, aluminum conductor cables. And yes, what are the properties? It can be lightweight, stiffness, strength, wear resistance. It can be anything. Fatigue, corrosion, tailor making of the properties, wear resistance, functionally graded material. That means what is functionally graded material? A material which has 2 different properties in one itself, something like that. You also can make a functional graded material. It's nothing great. So better properties than metals, ceramics, alloys, etc. Needs that composite. If we talk about food, I told you metal is sugar, milk, etc. Alloy is a coffee, and the composite, the powder metallurgy is also a given example. And the composite is fruit salad and sandwich. That means the constituents of the composites can be separated. For example, if you take aluminum conductors, you can cut and you can remove the inner steel wire. Why? It is only just physically mixed, only it is touching each other. Whereas if you make a silver copper alloy, if you make a steel, can you separate that silver and copper once if it is made into alloy? No. Can you separate the carbon from iron? No. that is inseparable, that is homogeneous mixture, that is solid solution. Whereas this, you can separate it. Composite can be separated. Something like RCC, you can break open and open your steel, cement, all these things you can separate. Another thing, when you make an alloy, the individual metallic properties are changed. We are getting a new property. Whereas in composite, we know that the individual constituent properties are retained and a combination of those properties we will be getting. So now if you see the structure wise, this is what is an alloy. We have already seen. Composite means it will be like this. It is only just touching each other. Mixed, physical mixture. Physically distinct. And there is one more word left out. Ceramics are compound. What is compound? We know that. For example, if you take any ceramic, aluminum oxide ceramics, or any other crystalline compounds, salt, let us take NaCl. This structure will be like this. You can see the difference. See, this is random, is it not? If you are making an alloy, it is a mixer and unit cell is homogeneous, but whereas there is some randomness. Is it not? Here, it is perfectly separate each other. Whereas in compound, the unit cell level itself, it will be fixed composition and perfect. I told you a few minutes back what is phase. Let us say iron and carbon. Pure iron is also alpha phase. Iron with 0.1% carbon is also alpha. That is also steel. Iron with 0.2% carbon also is alpha, and that is also steel. Is it not? Up to certain limit. What is that certain limit? That is solubility limit. Up to that solubility, it is always alpha, it is always alloy. Alloy can have various composition, is it not? 0.1% carbon, 0.2%, 0.05%, anything. So that is what is the randomness. That is what is an alloy. Whereas in compound, it cannot be. You know that. And the structure will be like this. Now we are coming to a new topic, ceramics. Okay, let us, if we talk about composite, what are the composites? One is polymer matrix composites, all plastics. That is polymer, and what are the reinforcement? It can be glass fiber. It can be another polymer fiber also. It can be carbon fiber. It can be natural fiber. It can be steel fiber. Is it not? What is steel reinforced composite? Is a vehicle tire as a typical example. Vehicle tire is a typical example for steel reinforcement. That is polymer as a matrix. Inside can be anything, metal, non-metal, ceramics, anything. And another polymer, what is that another polymer? Metal matrix composite. Metal is matrix, reinforcement can be another metal or ceramic, glass, something like that. Is there any example? Yes, we will come to that example, that is tungsten carbide 2. Or if you take about the aluminum conductor, that itself is a metal matrix composite. Aluminum is a matrix and steel is a reinforcement. That is also composite. Okay. What is another composite? Ceramic matrix composite. Ceramics matrix reinforcement can be ceramic, metal, anything. Then we should know what is ceramic. Ceramics, all ceramics are compounds. And their crystal structure, anyway, they are crystalline material. Non-metallic but crystalline material. And by look at this, you can look at this picture. This is aluminum oxide ceramics. Example for a ceramics, aluminum oxide, zirconium oxide, magnesium oxide, silicon carbide, silicon nitride. There are many examples we use daily also. Ramming mass is a ceramic powder. Oxide ceramic, carbide ceramic, nitride ceramic. Is it not? If you look at the gold coated watches, there are two types of gold coated watches. Real gold coated watches. Another is sometimes titanium nitride, TIN, titanium nitride coated watches. They also will have the same color. It's not that cheating, but they will sell only the brand of like gold coated watching. But if you look at the specs, if you buy a branded one, they will say what is the coating? It is titanium nitride coating. So nitride ceramics. So this ceramics, why are we talking about the ceramics? That is very high strength and ultimate, extremely brittle material. You just drop it from 2-3 feet, it will break into small pieces. They are also crystalline, but their bond, their structure is different from metals and alloys. That makes this material highly brittle, hard. So you cannot make this by any casting route, forming route, welding route. Why it is brittle? Automatically choice goes to powder metallurgy route. Only possible powder metallurgy route. Now you know metals, they are ductile, alloys, high strength and sometimes ductile. Now I given the example of ceramics. If you want, and you know the properties, what is the metal property and what is the ceramic property. Now, one more thing, if you just remember, it is carbon, graphite or carbon or diamond. If you want to combine all these things and get a new material that is composite, what is the process? What is the advantage? We know that advantage, certain properties. Now, if you want a composite, what is the process to make? That's what we are going to learn it. So where are we now? So metal matrix composite. We are coming back again to tungsten carbide tool. Most of you might have used or at least might have seen in a lab. People say carbide tool, carbide tool, carbide tool. What is that? What exactly is the carbide tool? See, carbide is a ceramic, is it not? Tungsten carbide, silicon carbide. These all are ceramics. Aluminum oxide, zirconium oxide, they are also ceramics. Oxide ceramics. Silicon nitride, titanium nitride, aluminum nitride, these all are ceramics. I told you the specialty of the ceramics. Highly brittle, it's something like glass. So where do we use ceramics? Whenever we want very high wear resistance or very high hardness or ultimate high strength, we are using this. No doubt in this. So what all are the requirement? Typical requirement is a cutting tool. Cutting tool should have ultimate high wear resistant and high strength. But unfortunately, can we use them as such? No, not possible. Why? They cannot take any mechanical load. That means they don't have any sufficient toughness. They don't have any ductility. We don't need any ductility also, but unfortunately, there is no toughness. But we need a material which is tough also, which can absorb a little bit energy. Same time, it should be high wear resistant also. Then only it will be able to cut that material, is it not? Then what do we do? There is no possibility of making alloy. And metal anyway, we cannot use it. Ceramic, though we can use it, but unfortunately it breaks into pieces. Then why don't we combine these two? That was the. For example, this is the microstructure of a carbide tool, tungsten carbide tool. Here, tungsten carbide is made into small powders. We are not going to talk about how to make tungsten carbide, that is a chemical route, and how to make tungsten carbide powder, that is also a metallurgical route. We can make the material carbide, you can make the tungsten carbide ceramic, and you can make it into powders also. Now, in the powder form, we cannot use it. You have to make it a component. And how do you make a component? And the component should have tough enough. So, you take a metallic material. Example for that is cobalt, or sometimes you can take nickel also. That also you make it into powder form. Now, in a record ratio, mix these two powders. Maybe something 75% tungsten carbide powder and 25% cobalt powder by weight. You mix it very well. Both are in powder form, it will mix very well. After mixing it, just look at the characters. Tungsten carbide, it's a high temperature and high strength. Cobalt, what is that high temperature means? I'm talking about the melting point. Cobalt, it is a ductile metal and the melting point is somewhere around 1455 degrees Celsius or 1495 degrees, somewhere in that range. Some approximately, let us say 1500 degrees Celsius. Okay, so if you want any casting of this cobalt, you have to heat up to above that melting temperature. But if you want to make any component using cobalt, you have to make the powder and you have to heat maybe around up to 900 or 1000 degrees Celsius, or at the best 1100 degrees Celsius. Okay, so first is making into powder, second is mixing and blending, third step is called compaction. Compaction is nothing but you're getting the shape of this mixed powder. What shape you want, that shape, and it should be solid, no, is it not? After that, it is heated to that temperature, that is called sintering. And sintering means there will be a lot of diffusion. Just to let us back to that atomic level like this, or let us go back like this alloy. When you heat it, these atoms will move here, that atom will move here, all the atoms will be jumping here and there. That's what is diffusion. Now, in this case, in between the cobalt powders, cobalt powder particles, there will be a lot of diffusion. That means all the cobalt powders will combine and will make into a single piece. Now, there will be wetting between this tungsten carbide and cobalt. What is that wetting? If you just put a drop of water on floor, that will wet. If you put a drop of water on glass, that will not wet, is it not? But here it will be wetting. That means there is a small thickness of liquid cobalt layer surrounding this. Now, this cobalt being a single piece now, all joined together due to the diffusion and heat, you assume that it is partially melted also. And there is a nice wetting between this and this. So all are joined together and kept together. Now you cool this product. After sintering step, you cool the product. You got a tungsten carbide tool, as simple as such. This is what is a composite. And you assume it. Cobalt we kept here. Instead of the cobalt is same. Instead of this tungsten carbide, you are keeping other powder. Let us say something like a silver powder or nickel powder or a tin powder. So we are heating to 1000 degrees Celsius, let us say. 1000 degrees Celsius, what will happen to cobalt? Nothing will happen. Only diffusion will happen. It will not melt. Why? Melting point is 1500. Now the second powder, it is, let us say, tin. What is the melting point of tin? Maybe 300 to 250 degrees Celsius. So at the temperature, tin will be completely liquid. Is it not? And that will go and get dissolved in this cobalt. So it will become an alloy. So if you want to make a composite between two metals, you have to be careful. They should not dissolve each other. Then only you will be able to make composite. If not, you will not be able to make composite by melting route or heating route. Okay. If you want to make a composite really something like tungsten carbide and cobalt, make sure that they don't react each other. If they react, then there is no tungsten carbide too. Is it not? There will be something else produced in this. So here we have to look at the 2-3 points. One is the combination of materials. That means which will get alloy, which will get compound, which will get wetting only, which will get reaction only, which will get diffusion only. All these things you have to look at it. Number one. Number two, anyway, properties, that is your wish. What property you want, you select accordingly. Is it not? Number three, the composition. That is how much percentage of this carbide, how much percent of this matrix. That is also depending upon the property. Now, after that, what you have to look at it? If it is for an advanced application or a strategic application, you have to look at the processing parameters and the equipments. What is processing parameters and equipment? For example, steel can be melted in air. Titanium cannot be heated in air. Why? Titanium will oxidize terribly and it will simply become ash. So it needs a controlled atmosphere, argon or vacuum. Tungsten cannot be heated in air at all. It needs a controlled atmosphere. If you want a copper also to be manufactured into composite, that also should not be heated in air. Copper will oxidize. So atmosphere should be proper. Then only you will be able to make composite for any strategic application. It's not like polymer composites, where most of the polymers are manufactured at a temperature maximum 250-300 degrees Celsius in air. Everything is done in air. Not like this forest application in space. Every material should be taken care in with respect to atmosphere. If not, Either they will oxidize terribly or they will lose its properties. So we will not be able to use it for those applications. So this is the main point, materials and atmosphere, that is processing atmosphere of the materials. That's what is this. Okay, one is processing atmosphere. Then what else we have to look at it? See, when you talk about the aerospace, naturally the temperature coming into picture, high temperature. Whenever high temperature coming into picture, you might have this in your any casting or any casting related products, and there is something called impurity or defect or an unwanted inclusions. There is no possibility of allowing any impurities in aerospace materials. So we have to maintain ultra high purity. That means all the aerospace materials are processed in a closed chamber or closed container, or it is called clean room. Yes. And other than these properties, two more properties to be taken care: creep and fatigue. Hope you know that what is creep and fatigue. Other than the strength, hardness, oxidation resistance, corrosion resistance, etc., etc., we have to take care about these two properties. That is nothing but creep is the high temperature failure. So when you make any material for aerospace, make sure that your material can perform the required load at the temperature, not at room temperature. So you have to test it also at that temperature. Then fatigue at that condition. And hope you know there is a difference between aerospace and aircraft applications. When it comes to aircraft applications, only for aircraft applications, particularly passenger jets, your factor of safety is important, very, very important. Why? Just take something like bridges, construction, etc. Factor of safety can go up to 10 also sometime, is it not? Any structure like that, parliament buildings or a pentagon like, they will keep factor of safety maximum, including it can withstand including the natural calamities. But what is the factor of safety in aircraft? Anybody remembers? This is just, it is something like meager business. Very, very less, 1.25, 1.5 in that range. But that is one of the least accident prone application, is it not? The least accident prone, number of accidents per unit is least in aircraft, aerospace. Why? If their accident happens, then that's all reliability goes. So there are two things. One, why the factor of safety is kept such a low? There is no other go. If you keep factor of safety 2, etc., weight will increase, or your aircraft cannot fly. Number two, to maintain such a tight property with such a low factor of safety, you can imagine how much stringent rules are there in the materials properties and testing of the material. That's why I told 100 rupees is the material means for aircraft application, 40 rupees is the material cost, 60 rupees is for testing cost. And they are processed with complex metallurgy. One of the complex metallurgy I told, it is atmosphere. Other complexities, we'll just look at it if time permits. We'll go as much as possible. Then the rest of the things you can mail me. The organizers will have my mail address. Okay, so first step is, let us start with alloying. We know that when you want to make an alloy, only route is you have to heat them and melt them and cast it. So after alloying, you know that casting. Next is, sorry, where is that? After alloying, it is forming and welding and machining, etc. For which application it is done for forming, etc., etc. That also we are not going deep into that. We know that. For example, any long section. For example, let us an aircraft, it's a fuselage, all long structures. Most of the things are made up of aluminum alloy. You know that aluminum alloy should be made into long product. In that there is a trick. The aluminum alloy cannot itself withstand its strength, that much high strength. So there are titanium fibers and titanium pieces embedded in it. So naturally it is a composite. So we'll come to that later. Yes. In alloying itself, if it is for an aerospace or an application which is a high temperature, For example, this is the composition of a superalloy. What is superalloy? I told you in a few minutes back, it is used in aircraft engines. And why we use superalloy? That is the only alloy which can take temperature as high as 700 plus. And that is one of the best known external combustion engine. And a material should withstand continuously few hours at that temperature. Means this is alloy is developed. We are not going deep how the alloy is developed, but this is a composition. You can imagine nickel, chromium, iron, molybdenum. Just look at it. This is 1500 degree melting temperature. This is something like 2000 degree melting temperature. You cannot melt it in air. Iron, we know it. Niobium 2000 plus this. And this also cannot be heated in air. Molybdenum, it is 2800 degree. Titanium 1700 degree. Aluminium 660 degree Celsius. So, and cobalt, carbon, manganese, silicon, phosphorus, sulfur, boron, all these things are there. If you do a simple casting like this for this alloy, that's all. There are some 13 different elements. Each one needs a different crucible and different atmosphere. How to make it? And just see the composition. You have to maintain a tight composition. For example, I'll give only one example, aluminium. That is something, here it is given, this is a textbook range 0.2 to 0.8, but let us say people will be stick to that only 1%, maybe 0.6%, let us assume. Everybody will use only 0.6%. What is the melting point of aluminum? Is 663 degrees Celsius. What is the melting point of this alloy? At what temperature it is melted? It's 1650 degrees Celsius. See, when an operation is carried out at 1650 degrees Celsius, you are adding a metal which is melting at 673 degrees Celsius. That to meager amount, let us say 0.5%. In 1 ton means it is only 5 kg, is it not? When you do all the casting, finally you check that composition, the 5% aluminum, 0.5% aluminum may be only 0.3%, 0.2% might have evaporated. Or during adding, if you done any mistake, small mistake, after making this alloy, you have to throw out the entire piece. Another one example is titanium. For example, titanium, Ti. The titanium problem, whatever crucible you use it, it will react with that crucible. See, there are only few possible crucibles. That means if you want a 0.65% titanium alloy, you have to add a particular higher amount of titanium in it, maybe 0.8% or 1%. That too, it will vary dynamically. So each one has difficulty like this. Then you have to melt it. After melting it, testing it. During melting also, people will test half the way. Make sure that composition is available. Then maintain this composition, obtain the property. Do you think it is easy? This operation is carried out completely inside a vacuum. That furnace is called vacuum induction melting furnace. So that's why this materials, this is one material. This material which is used in aerospace is very difficult. We are not able to make an alloy for these engines. Okay, so this picture I kept only to make you understand this is alpha and beta. What is alpha and beta? Alpha is a material with A and B. Majority is A, certain amount of B is dissolved in alpha, and B is vice versa, and in between is alpha and beta. And yes, so this is a typical picture of a furnace which is used to melt the aerospace alloys. That is vacuum induction melting furnace. This is the chamber, stainless steel chamber with a door. After closing the door, if you switch on the pumps, completely the air from inside will be removed. So it becomes vacuum. Then only the melting is carried out. For the melting, we need a heating setup, that is the induction. Hope you know the induction principle, something like induction cooker that we use in home. Same thing, but very high temperature capability. And the white color one is crucible. Whatever you want to add it, you can melt it. After melting, you are getting casting inside itself. And you can imagine the quality. See, the thing is, everything is closed. How difficult it is to maintain this composition. If everything is open, you can do something. Number one. Number two, when your operation is carried out like this, the cost will jump like anything, is it not? And number three, just look at this complexity. If steel can be made into 200 ton, 300 ton, whereas these kind of alloys can be made into 2 ton, 3 ton only. Size limitation is there. Why these many complexities are there? So these are the difficulties in vacuum processing. Yes. After making the alloy, if our headache over, no, not like that. You know that what is this? This is a casting microstructure with all chill things on the edge and columnar grains. Then the EQSP grains in the center. You might have read this. This cannot be used in aircraft. It has to be made into homogeneous. The only way out of making such an uniform structure, which is looking like in the right side, is by forging it. So to make the microstructure uniform, forging step is must. You cannot avoid that. We know what is forging. Yes. After all the forging and all your machining, all the things are done, you achieve the property. Heat treatment is also must. Can we use that alloy as such? No, still not possible. We have to make it as a composite. What is that composite? For example, this is an aircraft engine. And there are turbine blade inside, compressor blades and turbine blades. Let us talk about only that blades which are at high temperature combustion area. We know the alloy. What is that alloy? This is the alloy, super alloy. We melted it. What are all the difficulties? And we made the structure also uniform, and we made the heat treatment also. Still, this cannot be used because the temperature inside can reach up to 1100 degrees Celsius. That alloy cannot withstand 1100 degrees Celsius. Then what do we do? This is the thing what we are doing. This is the material which is used as an aircraft. That is super alloy. This super alloy is oxidized purposefully. What will happen? There will be oxide. And that is called thermally grown oxide. TGO, it is written here, thermally grown oxide. Only a thin layer will be oxidized. Then above that oxide, there is a zirconium oxide coating. This is a typical example for composite. The alloy, then there are two coatings. Above that, there is a composite coating. Sorry, above that, there is a ceramic coating. Now, the thing is, it is something like your gear. The temperature here above that is 1100 degrees Celsius, which cannot be withstood by the super alloy. So make a ceramic coating. What is ceramic? I explained earlier. And ceramic can withstand very high temperature. Unfortunately, ceramic cannot have any ductility. So let the ductility be taken care by super alloy, and let the high temperature characteristics be taken care by ceramics. But it is very simple to talk about it. Very, very, very difficult to make it. Why? Because you take a simple example. You take a steel plate in your home, or you take a copper wire in your home, and take a ceramic. Any ceramic, you take an aluminum oxide, or you take silica ceramic. Silica sand, you take it. Hope you know what is silica sand. Silica can be ceramic as well as silica can be non-crystalline also. If you cool very fast, it is glass. If you cool very slow, it is oxide again. It is a ceramic. That's all. So take that. Can you do that coating like painting? See, this is metal. Sorry, this is metal. This is ceramic. These two can never ever be combined. Can you take a steel and can you take a mirror in your house and weld it together to make a giant? Impossible, no? You know why it cannot be welded. But this is being coated by a method called thermal barrier coating. So this is another example for a high-tech aircraft application. Yes. So this will come back later. Yes, there are some other material, tungsten, molybdenum, tantalum. These all are used for very high temperature. So these metals are called ceramic refractory materials. These metals are called refractory materials. They are all made into powder metallurgy route. I told you already. Okay, and let us see another typical example of a composite. You might have seen few manned missions for space, and when we return, some of the manned missions, they used to get dropped on the earth. When it's getting dropped, it should absorb a lot of energy. when it has to absorb a lot of energy, the material should be also accordingly like that. So the typical example for a high strength material, but still it is ultra lightweight. It's not lightweight, it's ultra lightweight. It's called honeycomb structures. Typical example is honeycomb structures. It is nothing but you take a sheet metal. Just after the lecture, you can just open many videos are available in honeycomb structure. This is used in crash-proof vehicles also. So this I am explaining using a metallic material, but there are things in this manner in polymers also. Just like a honeycomb, take a honeycomb structure. This is a honeycomb structure with certain thickness, is it not? From the picture, I can assume that this thickness is something 10-15 mm, that's all. And this is something like 1 feet into 1 feet. This is made up of a superalloy. IN718 is nothing but a superalloy, which we explained previously. So this honeycomb structure, we take it. Above and below, take same material, 2 sheets. Now, combine the 2 sheets like this. See, there is a bottom sheet, then this is a honeycomb structure, and there's a top sheet. After combination, it is combined now. We can see the honeycomb structure in between visible. After combining, you join it. See, now the honeycomb is made. You can see the middle is honeycomb, top and bottom sheets are combined together. How it is combined together? The thing is, there is a welding process. This welding process is called brazing. So please remember this word brazing. Brazing is nothing but we are keeping another low melting metal foil here, low melting metal foil, and whole combination we are heating it to above the melting point of this foil, but below the melting point of this structure. What will happen? This will melt. This is being foil, there will be only little amount, so it will have a bond between these structures. Bond between these structures, metallic bond. So we made this honeycomb structure. So this is a typical example of it. This is lighter than water as a whole. Why? There are a lot of gaps. You see, lot of gaps. 90% is gap, only 10% is material. But strength will be near equal to a solid structure, near equal. This is one of the great invention by few scientists about the honeycomb structure. This is being used in nowadays used in automobiles also. This is another case study. So what are the case studies we have seen? The engine material, tool, honeycomb structure. Any other case studies there? Yeah, this is the microstructure. If you do the joining, that is brazing. This is one side material. This is another side material. The in between will be like this. So let us go back and see. Last topic for the day. Yes. Whenever you see an aircraft, you might have seen there are thousands of riveted joints on aluminum body. I told you that aluminum body is embedded with the titanium fibers, that is for high strength. It is not an alloy. You can ask the question, why titanium is high strength and aluminum is low strength, lightweight. So if you make an alloy, can't we make a structure while it survive? No, not like that. See, that must be composite only. Why we cannot make alloy? Once if you make an alloy, we know that we have seen that certain properties will be lost. Is it not? We need lightweight and ductile aluminum alloy. We need high strength titanium alloy. If you make separately, we need. And when we make it a composite, both the properties are retained. Is it not? We need ductility. We need lightweight. We need high strength. All these properties are retained. If you make an alloy among these two, then that's all. It will become brittle. High strength, but it will become unfortunately brittle. Okay, so leave the topic there. Let us come back only to the aluminum alloy. Aluminum alloy structure. Aerospace material is only one particular type of aluminum alloy, that is aluminum copper alloy. Let me explain from here. Yes, consider only this is a phase diagram. Phase diagram is nothing but a temperature versus composition diagram. Here it is explained with the help of copper and silver. So aluminum copper for aircraft application is 95.5% aluminum, 4.5% copper. In industry it is called duraluminum. So that aluminum will have an alpha structure. We know what is alpha. Something it will be like this. And there is no beta in aluminum copper alloy, it is only theta. So alpha and theta will be there in aluminum. So let us go to that aluminum. Yes, this is alpha and this is theta. Hope you are aware about the phase diagrams and solubility limit, alpha, single phase, multi-phase, etc. How are we made this? How do we make this alloy? First step is alloy making, I told you already. You have to make aluminum and copper as an alloy. And why pure aluminum cannot be used? We don't have sufficient strength. We have seen in the first few slides, alloy is made only to make high strength. And why only 4.5% copper? Number one, density. Number two, if you keep on increasing copper percentage, ductility will be lost. So we need a strength in a particular manner. So we are adding copper. We are making alloy. I told you after making alloy, you have to do forging. Why? Making uniform microstructure. After forging, it is made into record shape, maybe thin sections, round pieces, square pieces, X, Y, Z, whatever you want, you make it. If you want any farming, drilling, sheet metal, whatever you do it. That is, you know it already. But the thing is, how are we getting high strength in it? Just look at it here. This is a typical casting. The last picture is something like typical casting. What all are they? One is alpha. Alpha is nothing but certain percentage of copper is dissolved in aluminum. And there is a theta. It's a two-phase alloy, is it not? Alpha and theta are there. Theta is nothing but it is a compound Al2Cu something or Alc2. There is a compound theta. And this compound is called intermetallic compound. Why? It's not a real compound. It is not a metal also. So intermetallic compound. The difference is alpha is a phase. Alpha can have certain amount of copper in it, maybe 0.1%, 0.2%, whatever may be the case, it is alpha, you know it. And this is grain boundary, there is no dispute in that also. But the matter is theta, how the theta is present in it. In the casting, let us say it will be something like this. Then it is forged. After forging all other operations, it is heat treated. Heat treated means just look at it here. If we heat this alloy to somewhere around 500 degrees Celsius, there is only alpha available here. There is only alpha. What does that mean? Where is the theta? Theta is dissolved inside alpha in that temperature. How it is dissolved? It is there in room temperature. How it is dissolved at high temperature? It is something like sugar and water. When you heat the water, you can dissolve more sugar, is it not? Like that, we heat it to 500 degrees Celsius. Naturally, automatically, the theta, that intermetallic compound, is broken and the copper is completely dissolved in aluminum. Copper is dissolved in aluminum. That is, alloy is made. And we know that what is alpha. And there is a character for this alpha. When you heat it, that alpha can dissolve more copper. When you cool it, that alpha can remove it. They can send out the excess copper. That's all. So when you heat it, excess copper is dissolved. So only one phase is there, alpha. When you cool it, theta also will precipitate out. Why? At that room temperature, solubility of copper and aluminum is less. That is known from this. Using this metallurgical character, what are you going to do? You make this alloy, then you heat it to this temperature. Instead of cooling, you quench it. If you are quenching is nothing but putting in water. That means you don't give any time for theta to precipitate, theta to form. So only alpha. But what is that alpha? It is an excessively copper dissolved alpha. It is super saturated. Super saturated means we forcefully dissolved excess copper in aluminum. But we know that this is not a stable structure. It's not a stable structure. Just heat it to somewhere in between 150, 160 degrees Celsius. Already it is overstressed. Lot of energy is inbuilt. Now we are giving thermal energy 160 degrees Celsius. That will make this theta to precipitate out. That means excess copper which is forcibly dissolved in alpha will come out in the form of theta. Not pure copper will come out. It will come out as a theta form. It will come out. that theta will be something like this. You see this picture, ultra fine size theta distributed evenly like this. If you correctly control it, it can be nano size theta also. Now, why are we talking about this? This particular combination, this particular heat treatment only will give highest strength of aluminum alloy. For example, pure aluminum has a strength of around 70 megapascal. Aluminum copper alloy, what we are talking about, if you only do casting, it is around 100 megapascal strength, only 100 megapascal. But if you do all this heating to this temperature, quench it again, heating this 160 degrees Celsius, and control this theta precipitate, it can have a strength of 400 degrees Celsius, 400 megapascal. So from 100 megapascal of this alloy, we made 400 megapascal, 400 times, is it not? 4 times, sorry, 400%, 4 times more strength we got it. This is how we get high strength material for aircraft. And now we are coming back to the question, why aluminum in aircraft is riveted, not welded? Just imagine, how do we made this? We heated this temperature and cooled to this temperature and again reheated somewhere in between and got this. Now, if you weld it, what is welding? Welding is a mini melting, is it not? Mini casting. So, if you weld two pieces, that place it will get melted and it is casted, it is cooled. So weld place and nearby heat affected zone will be something like this, no? The cast structure, the last picture cast structure. What is the strength of this? I told you already is only 100 megapascal. So entire portion is 400 megapascal. Only near welding it is only 100 megapascal. Can use it in aircraft? Impossible. It will get collapsed. So this is the reason why are we not able to make an aircraft structure by welding. This is the actual reason for aluminum alloys. People will say aluminum alloy is not weldable, that is not weldable. Why? There are 4 or 5 reasons. One among the reason, that is the metallurgical reason, is this one. If you weld it, you will not get the structure and you will not get the properties what we obtained. But is there any solution? Imagine, anyway we have to weld it, no other choice. Yes, we can do it. You weld it previously, then only you heat it. Is it not? Weld it, then after welding you heat it. Don't do heat treatment first itself. Then you can again ask, then why nobody in the world is able to make this like that? Let aircraft manufacturers weld it and heat it. Why nobody is doing up to now? That's not that simple. Why? Because there is no furnace in the world which can heat it that much size of that aircraft. Is it not? Very, very difficult. You will not get the uniformity. And once the structure is made and if you do heat treatment, that's all. Mechanically, you know it. There are thousands of stresses, bends, deviations, uniform, ununiform, X, Y, Z. So finally you have to dump it and scrap it only. Is it not? Okay. So for the time being, I'm just stopping this. If you have any doubt, you can switch on your mic and I'll be there in online as long as all your doubts are getting clarified. And if you have any other doubt, if you are working in, someone is working in metal matrix composites, metallic sites, ceramic sites, composites, cermets, etc., something like I told you, why electronic gadgets are coated with nano gold and how that nano gold is there. There are hints in the PPT itself, PVD, CVD, like that words. So all those things you can contact me always using the mails. So as organizer, anybody is online?
Sir, good afternoon, sir.
Good afternoon. So anybody has a doubt, you can.
Sir, only one thing, sir. Sir, I am working on aluminum metal matrix composite.
Okay.
One thing now, when we are discussing in polymer, my friends are doing on your polymer.
Okay.
They are being reinforcing that steel with epoxy.
Okay, you are reinforcing steel with epoxy or epoxy with steel?
Just they have been having, they are going for hand layup only, sir. What they are doing is they are placing just a layer of resin, then they are placing that steel mesh. Once again, they are layering a machine and their orientation changing. Like that, like we can do in aluminum metal matrix, sir.
Aluminum is matrix, and what is the reinforcement?
in the reinforcement, for example, there what he has been asking me is we can mix aluminum and silicon carbide as a reinforcement. In aluminum, silicon carbide can be used as a reinforcement.
The thing is, when you are doing hand layup, and when you are mixing two things and applying, your application condition parameter matters, is it not? That is being polymer, he is able to do at room temperature and he is able to do handle that is liquid condition. But aluminum, it will be liquid condition only at 700 degrees Celsius.
That's why, sir, we have a furnace. We have a strip casting furnace. We just melting. He's been asking that in the die, if we have that mesh can be placed and we can pour aluminum, steel mesh.
Yes, steel mesh can be placed and it can be poured, but not as simple as such. There are you have to 2-3 things you have to look after it. One is steel mesh and die, all those things should not be at room temperature, number one. Number two, there should not be any air gaps present in it. Number three, the steel and aluminum will react and it will form some unwanted intermetallics. So please note down my email ID and ask me, and I will give the guidance how to do that work. We need to do in a particular parameter, not simple casting will work for that combination.
Okay, sir. I will be getting you in touch with your email, sir. Thank you, sir.
Sir, I am Ram Gopal Reddy from Guntur. Sir, what are the different manufacturing methods which are available for ceramic matrix composites? Ceramic is the matrix and ceramic also reinforcement. So these are having some major applications in aerospace. So what are the manufacturing methods which are available for manufacturing these composites?
When we are talking about the ceramics, if it is a conventional application, we know that only powder metallurgy. Okay, then what is for aerospace? What is for that any high temperature application, etc., etc.? You can use a chemical vapor deposition. Or high temperature powder metallurgy, something like hard press. Chemical vapor deposition, some extent physical vapor deposition. Nano in situ synthesis. Whenever it comes to ceramics, you can use a synthesis. And you can do anyway joining also. It depends upon your combination and your component. If your component structure is a solid, one side metal, another is ceramic, another ceramic, you can use any fabrication, something like joining, bolting, riveting. There are thousands of methods, but CVD is one of the most famous thing which is used.
Okay, thank you.
Yeah, someone is asking a mail ID. I don't know whether rajuntdc@gmail.com. Let me share once again. And if any question is there, the organizers may read it.
Hello, sir.
Yeah, is it my slide visible?
Yes, sir. Yes.
Yeah, rajuntdc@gmail.com, 720-735-9461.
Sir, I have a question, sir.
Yes, please.
Is this aluminum copper alloy naturally aged material, sir?
Yeah, see, the thing is, when we want to use it in aircraft, it's artificially aged. Naturally aging, purposefully, if you want, you can do that. Is aging, but aging is nothing but a heating at 160 degrees Celsius. You may be aware. Why are we doing an artificial aging? We want the things to be done quickly. 10-12 hours, so the precipitate, theta's precipitate should form. If we allow natural aging, the number of precipitates will be less. Number of precipitate will be less means automatically the size of the precipitate will be more, no? When the size of the precipitate is more, the mechanical strength will be lesser. That's why natural aging is not preferred.
Okay. So one more question, sir. What's the difference between cast alloy and wrought alloy, sir?
It is very simple. Yeah, cast alloy is something like, what is the difference between a biryani cooked as such and what is the difference between the biryani cooked after that and using a tawa? You are kindling it very smoothly, making it uniform. Something like cast alloy is only cast product. Wrought alloy is formed one. You are forging it, rolling it.
Okay. Okay. Thank you so much, sir.